Ladies and gentlemen, I'd like to start today's keynote presentation. It gives me great pleasure to introduce Renee Lagos from Chile. Renee is Chairman and Chief Executive Officer of his own company, Renee Lagos Engineers, and leads the firm's high-rise buildings and seismic design group. He's been responsible for the structural design of more than 1,500 projects, representing over 12 million square metres of building area for buildings up to 64 stories high. He's designed the tallest building in South America, the Costanera Center complex in Santiago, which I had the pleasure of visiting in January. And that 700,000 square metres complex, with the main building being 64 stories and 300 metres high. It's quite something. And he's designed the tallest residential building with seismic base isolation in the Americas, a 32-story building. I had the pleasure of meeting Renee in Santiago at the 16th World Conference on Earthquake Engineering in January. And Renee gave a fantastic keynote there, and I thought, there's so many messages in here that are relevant to what we're facing here in New Zealand, and I'm sure around the world, about how we design buildings and how we make sure that they not just survive earthquakes, but are resilient and keep damage to a minimum and make them repairable. And I remember having a discussion with them about whether it was, almost tongue-in-cheek, whether it was possible to design an earthquake-proof building. And Renee says, well, and how many of us are reluctant to say that that's possible. Well, he has a slightly different view, and I hope he might give it to us today. So I won't take any more of your time. Renee, please come and give your keynote.
Thank you, David, and thank you, Peter, and thank you, the organizing committee and the society for inviting me this afternoon, making possible to present you some experiences that we've had in seismic design of buildings. So my presentation today is going to be about the quest for resilience in seismic design of reinforced concrete buildings. And by presenting the Chilean practice, I will intend to show you how important is the stiffness approach in order to get resilience behavior. Okay, so what will be the question that I will address in my presentation? First of all, what is resilience? When do we set the performance standard in a project? What is damage? What is an acceptable level of damage for buildings? What are the possible strategies to achieve resilience? And I'll speak about the Chilean practice and go to final remarks. Okay, so what is resilience? Probably the simplest definition of resilience would be the ability to recover and return to normal functioning after adversity. So we're speaking about functionality, retaining and returning or recovering to functionality. So probably the opposite to functionality, it would be damage. So if we think of damage, then the possible strategies in building design, in seismic building design, would be, first of all, try to avoid damage. Sometimes that is too expensive and we cannot do that, so we have to move to a loss and damage that is essentially repairable. This is in the majority of the codes as a philosophy at the beginning of the seismic codes throughout any country in the world. Additionally, you will find there the following words, says, avoid collapse. It is important to mention that if we are speaking about resilience, the avoidance of collapse, although it is a major issue and a very important one, it is a life safety issue and not a functional issue. So we're going to focus on the two first in order to speak about resilience. So the big question is, when do we set the performance standard in a building when we work on a project? When we start working on a project, we can distinguish usually two big phases. The first one is related to the conceptual phase, where based on concepts and strategy, the structural engineer simply makes the definition of the structural system he wants for this particular project. And then comes a second one, which is the largest one, where you do all the analysis, design, and detailing of that structure, which is nothing else than the implementation of that strategy. The important thing that one must be aware is in this first phase, the structural engineer is absolutely free to select whatever he thinks is best for the building, the best alternative of structure for the building. So this freedom and his choice is based generally in engineering ingenuity, and is limited usually by local construction practice, which is one of the biggest problems in order for the structural engineer to be really free to do whatever he thinks is best. On the second one, there's no more freedom. On the second phase, the structural engineer is faced to follow the code strictly. So the statement I want to make here is that good performance starts at phase one. Before you get into the code, it's when you have to make the definition of the structural system for your building. So now let's move to what is damage. There are different types of damage. You can think of structural damage, non-structural damage, and content damage. If we go through structural damage, we leave out the shear failure type of damage because it's brittle and we don't want it in our buildings because it's not it's dangerous. So as long as we think of flexural damage, damage is, you can see there in the image, the strain diagram of what's in any section subject to flexure. Damage, it is related to strains. Every time the strains in our section goes beyond certain values, like around 0.3% for concrete and 0.2% for steel, we start collecting damage. So if we think of frame type structure, damage will be located on the plastic hinges wherever they are in the structure. And those plastic hinges appear depending, it is related to the roof displacement and the height of the building, which we will say is roof drift. If we think of wall type buildings, damage will be located at the critic section, usually at the base of those walls. And you can also find here a relation between the roof displacement and the strains in the concrete at the critic section. In the case of non-structural damage, non-structural elements usually are not continuous throughout of the height of the building, but rather they exist only in between two consecutive floors. So in this case, damage is related to interstory drift rather than roof drift. The important thing to note is that interstory drift, it is related somehow to roof drift, depending on the type of a structural system that you use. If you use frames or you use wall type, here you see what are the elastic of those, the shapes of the elastic of those type of lateral systems. You will get much different interstory drift for the same roof drift. Actually, you are going to get much higher interstory drift in case of frame buildings rather than shear wall buildings. And this is an important knowledge to have present when you are thinking of what is the best alternative in the first phase to structure your building. And finally, content damage is related to story acceleration. So if we're thinking about resilience, we should try to control or have the minimum damage of these three types of damage. So the question is, can we reduce all three at the same time? Is this possible? And to understand the answer to that is simply by looking at this displacement spectrum, acceleration spectrum. You can see that when you want to reduce the roof drift, you have to move into very stiff structures. But if you select stiff structure, you're going to get high acceleration. So the answer would be, if you reduce A and B, you increase C, and vice versa. So no, you cannot, with conventional structure, solve the three type of damage simultaneously. You would have to go into the use of some special seismic protection devices. In that case, you can control the three of them, as we will see later. So now, what is an acceptable damage? That is a big question. Historically, I'm sure you're all familiar with this matrix, which was proposed by CIAOC Vision 2000. This represents a relation between performance objective and the earthquake probability of occurrence, where according to, depending on the type of use for the building, you define a certain basic objective, which would be an acceptable level of damage. The important thing here is that the parameter that is used to quantify this is the drift, H over D over H. But this is just one way to quantify the performance. But should we do it from the perspective of the structure, or the people, or society? And why am I asking the question this way? Because it depends on how you, who are you thinking of? The answer to this question might be different, as we are going to see on the next pictures. Of course, when you have no damage, that's the ideal case. There's nothing to discuss about that. But what happens here? Here we have a picture where it shows minor content damage, but no structural damage, which, by the way, is a picture taken in our office in the upper 2 floors of the buildings you see on the bottom. This is just, computer monitors overturned, books out of the shelves and things like that, but nothing seriously that it took us a day to recover functionality again. So, but what about this? In this case, we have non-structural damage in non-structural components, which is, you can see some gypsum board cracked, and no structural damage. But please take a look at the picture to the right. If we look at that, those are major cracks affecting non-structural component. But what if behind those walls you have a bathrooms or maybe a kitchen? Probably the owners of that apartment will not be able to stay living, go on living on that apartment. It will have to be evacuated. Is that an acceptable level of damage? From the structural point of view, it is. From the people who's living there, from the social, it absolutely not, because you might think what would happen if you have 100 buildings in that same condition. So another example would be these cases of structural damage, which are pictures that came out of our last earthquake. Of course, in case of this structural damage, big buildings would have to be evacuated, and this is not acceptable from a resilience point of view. More structural damage, very impressive, some of them. And of course, something that is totally unacceptable, it is collapse. Okay, so if we want to take a deeper look into performance, let's look to what the performance index, which is roof displacement divided by the height of the building, means. We can always, run the numbers and see what's the performance index for one of our buildings, but the idea is to understand what are the variables involved behind this parameter in order to be able to use that knowledge in the first stage, in the conceptual stage, before you run any numbers. So in order to do that, we can start out with the roof displacement spectrum, which is something that is on every code, on every country, seismic country. The roof displacement spectrum is usually a bilinear, has a bilinear form, like you can see that in the picture. And if you divide that by h sub 0, you get the expression to the right. And if you move the term in parentheses to the left, you get the bottom expression, which is very interesting because it has 3 terms. The first one is the performance index, which is what we are trying to understand. The second one is a parameter which is h over t. H is the height of the building, t is the crack period of the first mode of the building. So it's those two, h over t depends only on the structure. So, and you can think of it as, it has units of velocity. And you can think of it as how quickly the building reacts to the shaking on the base. And the quicker it reacts, it means the stiffer the structure is actually. So that's why we have called that parameter stiffness index. And the third parameter there is alpha, which is a site index, because as you will see there, it is related to the type of soil under the building, and the seismic zone actually in that parameter is involved the seismic demand. So y times 6 equal a constant represent a graphic like the one we are seeing here in the right, where any building located in the ascending line to the left would be located over the line, the curve on the right, and any building in the horizontal part of the displacement spectrum would be on the yellow area here. So the performance spectrum is nothing different than the displacement spectrum, only that you have plotted into different variables. So if we look to this image, we can realize, for instance, that a very efficient strategy in order to increase the performance index would be simply pushing your building to the right. By increasing the value H over T, that means by increasing the stiffness, you will get a much better seismic performance. A horizontal line on this graphic would represent a performance level. And one of the, so far this graphic represents an approach starting from roof displacement or displacement demand. We can think about this, about performance from a different point of view, which would be from energy dissipation, which is something that was proposed by Dr. Mario Rodriguez and with his damage index. What he did, it was simply, the damage index is related to the hysteretic energy dissipated by an inelastic single degree of freedom model. He evaluated that for several earthquakes, for several periods of structures, for several type of lateral load system, like frame buildings and shear wall buildings, which are represented by the H over T. And this parameter with a value of 0 represent an elastic behavior, and with a value of larger than 1 represent the potential of collapse because you're getting damage. Also, one of the variables considered is ductility, which you can think of it about dumping in a way that how much inelastic behavior is acceptable within the building. So if you want elastic behavior, of course, you're going to get a much higher response of the building. Okay. So here's another images of the same evaluated for an earthquake in Chile. But let's compare these two approaches. If you look at the one on the top, performance and the damage index, they are pretty similar in a way that if we, in the vertical axis are both indices, and the horizontal, if you look at what H over T says, they're almost identical. The interesting thing about these graphics is that you identify somehow 3 of the most important variables that are related to performance, damage, or maybe resilience. One of them is the value H over T, the second one is the natural period of the structure, and the third one is ductility and damping. If we are dealing with conventional structure, the most effective way is just using stiffness, increasing stiffness. Why? Because you cannot be certain if you use the second alternative that by increasing T, you're going to move exactly, maybe you will end up in the zone with the highest value. So you have an uncertain way, and you have to deal with the interstory drift issue like we mentioned before. And of course, if you want to increase ductility is synonymous of damage, so it's not a practical way in conventional structure. But if you decide to go and use seismic protection devices, you can provide damping by using some damping system, for instance, and that way you will concentrate and all of the energy dissipation in one element, and you will not require ductility to the rest of the structure, which is a good idea. And the other alternative would be to use base isolation system. If you do that, what you're doing is adding a soft story where you will lengthen the natural period of the building, which would be the second strategy. But the interesting thing is you're solving the drift issue because you will concentrate all of the drift in the level where you place the isolators. So you can see that depending on the type of strategy you're going to use, always these are the 3 most important or most relevant variables associated. Now let's take a look at the Chilean practice. Within 1985 and 2010, which is 25 years between the 2 largest earthquakes that we've had in the central zone of the country, Some 10,000 buildings were built, according to that statistic. Out of those buildings between 3 and 55 stories high. Of those buildings, 20% had 20 stories, 9 stories or more. And statistics say that the buildings that collapsed were 5 in 2010. And the buildings that had to be demolished due to damage were 40 approximately. So the statistics say that 5%, between 1 and 2% of those buildings did behave, were failure cases. The rest of the structure suffered non-structural damage and in some cases minor repairable structural damage, which is, in a way, you can say it was a very successful performance. Let's take a look at what the performance index tells us about this. Gendelman took a database of more than 2,600 buildings, real buildings that were designed and built before the 2010 earthquake, and reanalyzed them considering the displacement observed in reality during the earthquake, and came out with these values. Every blue dot there represents a real building, and you can say that below 0.5%, which represent operational behavior, are 88% of those buildings. So this value would give, I mean, a very good correlation with what statistics tells us that was what really happened. Now, the important thing is that it didn't mean that we were doing everything right, as we will see later. But so we had to make several changes on the code, and one of the things that was important for us, that we wanted to correct the mistakes usually related to detailing, but we didn't want to change the way our buildings were structured and had a general behavior. So here I plotted on red 198 buildings that were designed and built after the 2010 earthquake that were designed in our firm. And you can see that those dots coincide very well with what it used to be. It means that we haven't changed the way we structure our buildings or the behavior of our buildings, but only the detailing of it. So as a summary, although that 2010 earthquake, which is a magnitude 8.8, it is actually the 6th largest earthquake instrumentally recorded by history. And it is hard to imagine something stronger than that. The usual objective should have been life saved. Nevertheless, the observed objective was actually operational, which is quite good. Let's take a quick look at what is the local practice regarding to buildings. We can see here we have flat slabs. We don't usually beams inside the plants. Usually we have a lot of shear walls. Let's go and see some images. I'll go quickly through this. You can see many shear walls, frames at the perimeter, not too many frames. Shear walls are coupled, forming shapes, L shapes, C shapes, and then T. And in the case of office building, we concentrate those walls in the core. So, thinking of phase one, how do we structure our buildings? In generally, like you were saying, we're using concepts and strategies. So the strategy is usually to make extensive use of shear walls in each of the principal directions. Those buildings you just saw had redundancy, had an important wall density, had walls of shape L, T, and C. And if we think about what are the positive and negative sides of this alternative, redundancy means safety. It gives you additional lines of protection. When one fails, you have a second and a third one, and then maybe a fourth one, and that prevented us from our buildings from falling when we had some problems. It has no negative side. Wall density, it helps you to reduce stresses, compression and shear forces in the building. And the negative side is you get stiffer buildings that might give you larger acceleration, even though in general, in our building, acceleration hasn't been really an issue. Wall shapes of L, T, and C form also increase stiffness, but the problem with that is sometimes it's difficult to design for ductility in the borders of those walls. So, no, I went back. Trying to understand what are the characteristics of this building, historically we have used certain index that allow us to quantify these types. One of very simple index is the wall density index, which is somehow the wall area in each of the principal direction divided by the weight of the building above that floor. This is the graphic of historical values. You can see there's a decrease in the average value, but the important comment is not the average value, but rather the minimum. There's always a minimum that we never go beyond that, which is 0.1%, because it is being experienced by us that that number gives us good protections against drift and give us very stiff buildings. So now if we think of the inverse of the wall density has units of square meter divided by tons. The inverse of that would represent, it is related to the average of compression forces on those walls, and also is related to shear forces acting on those walls. So it's a very, we can draw a lot of information out of this kind of index. If we want to think it in a simpler way, usually buildings have a unit weight per floor area of 1 tons per square meter. So if we replace that value in that formula, we would say that the wall index is simply a relation between areas, between wall area in the first floor to floor area above that floor. If we think of that, a simple rule of thumb that we usually use to structure a building is provide 1 square meter of wall area per every 1,000 square meter that you have of floor area above that, okay? Now if we think of the stiffness index is the parameter like we call H/T. This is a graphics of buildings designed and built before and after the earthquake. For us, normal stiffness, our stiffness H/T higher than 40, and flexible buildings, usually frame buildings, would be below 40. And a very stiff building would be between 70 and above. So that is the type of walls and structures that give us the level of performance that we observe on this graphic. So, but the big question that many times is asked to us when we speak, when we tell these stories to people from different countries, the question is how much money you spend by doing this type of structure. So I just want to show you some comparison of what are the concrete ratio index and the steel ratio index. Concrete ratio index is how many cubic meters of structural concrete are we using per usable square meter of area. In a way, we can call this also the equivalent slab thickness because it has units of length. If we look at this graphic, it shows different type of soil, but it's related to 128 buildings designed and built after the earthquake. They have been done by our firm. And you can see that, let's say for a 20 to 25 story building, you get an average of 0.35 meters of equivalent slab thickness, which is, according to the practice, at least in Latin America, very common, very used. There's no, we're not spending more money on structure, on concrete structure than anybody else is doing. If you think of a steel ratio index, here you have how many kilograms of steel per square meter. And again, if we go to 20 to 25 story, you get 35 to 40 kilograms of steel per square meter of usable area, which is also very reasonable. I've chosen to compare it with this graphic that I took from the Council on Tall Building Journal that was published some years ago, even though it was meant for steel buildings. But you can see if we place the numbers that I just showed you with the Chilean practice, they fit right in the lower left. So being in the left, it means that it is a very, let's say, efficient way of spending money in structure. Now if we move to phase 2, which is code. What are the code requirement that we have. In order to understand that, what is the philosophy behind this, it is important to know that being Chile one of the most seismic countries in the world, we have in our history more than 30 events of magnitude 8 or higher. Actually, we have an average of 1 every 15 years, but only in the past 10 years we have had 3 of those events. So it means that we think of big earthquake as something natural and not just a probability. One of the problems that you already are aware of, I'm sure, is that when you have those big earthquakes, subduction earthquakes, they affect they have a rupture length very long. So it means it affects several cities simultaneously. Just an example, in 1960, 9.5 earthquake, Valdivia had approximately 1,000 kilometers length of rupture. 1988, Valparaiso, 8.0 magnitude, 220 kilometers of rupture length. 2010 Maule earthquake, magnitude 8.8, 500 kilometers. So again, many big cities in the case of our country were affected simultaneously. So in reality, what we have assumed that for any given building that we're going to design, the design earthquake will take place at least once in the lifespan of the building. It's not a matter of probability, it is a certainty. I can tell you of the, I don't know, more than 1,000 buildings that I have been responsible for the structural design in my engineering practice, I can tell you that probably close to 1,000 buildings have been subjected at least once and many twice to some of these magnitude 8 or higher. So one have to be very careful because society will make you accountable for the things that you have done. For this reason, every time we have an earthquake, we upgrade our code in order to trying to obtain immediate occupancy. Why is that? Because people used to be very thankful for structural engineers that they saved their life maybe some 50 years ago, but not anymore. Now they're asking immediate occupancy. They don't want their lives to be disrupted by damage in their buildings, even if you're speaking about the largest earthquake on Earth. So this is how many of our cities, especially around the coast, looks after an earthquake. You can see there's a lot of damage there, but most of that damage, what we're seeing in the picture, is related to very old houses, adobe houses, unreinforced masonry houses, building type of construction that have not been done by structural engineers. But nevertheless, if we think of new construction, we did have many problems, as we can see here. But I just want to share you very quickly what are the lessons that this building tell us after the earthquake. The first thing that those buildings severely damaged, half of them had failures that can be attributed to subclassification of foundation soils, resulting in larger displacement demand than those that could have been anticipated by using the code. So we have to fix our code after the earthquake. The other half of the buildings had failure that could be attributed to structural reasons that could have been avoided. This is important. One of them was poor structural detailing, so we had to improve also the way we detail. We did, the use of boundary element wasn't enforced on our code until now. Now we changed to that, and construction mistakes. Another issue that is important to mention is that the majority of the damaged building had their first natural period of vibration with values around 0.6 seconds. That means buildings of mid-height. We will see later why is this problem. Our codes do not have explicit prohibition to use irregularities. So one of the things that you could easily notice by looking at our structures is that we use them, unfortunately, very frequently. And many of the damage, the observed damage, occur around the concentration of stresses on those areas. One of the typical things that we have to use because of structural and owner's requirement is what we call flag length, which is the reduction in length of the walls in the lower floors, usually underground, because of parking requirements. The client says no parking, no building, so you better come out with an intelligent solution about this. And these are the kind of problems that we have encountered in those reduction where we get a concentration of stresses that produce some crashing of the concrete. So what are the changes that we made out to our code? In the loading code, we address soil issues like we have to change classification, we increase the spectrum for soft soil, we include amplification effects. And one of the important things that we decided in order to control damage, we define a roof displacement, an ultimate roof displacement, which we call delta U, which represent the observed roof displacement in the 2010 earthquake. We're going to use that displacement, roof displacement, in order to control damage, as we will see in the next slide. In the concrete design code, we made changes. We limited the slenderness of the shear walls. We limited the maximum compression on walls. We limited the maximum concrete strain to 0.8%. And this has to be achieved when we displace the roof in delta U. We require a minimum thickness of 30 centimeters for boundary elements and so on. So our code is no different than most of the codes in the world in a way that we have to do model spectrum linear elastic analysis. The design loads are the elastic response loads divided by R factor. And then we have to comply with the minimum base year, and we have a very strict drift control at the center of mass and the perimeter. These two last requirements, the base year and the drift control, are actually the responsible for the stiff buildings that we have. Performance-based design hasn't been in our code so far, even though it's going to be in the next version, because we already have a draft finished for discussion. And it's only been used historically on a limited number of projects for certain special cases. I'll go quickly through what is the acceleration spectrum and displacement spectrum. They have the typical shape that you can find on any code. The important thing I was mentioning, that these two spectrum correspond to different earthquakes. The one in the left is what we use for strength design. It's been what historically we have done. The one in the right, it was fixed and upgraded to the displacement that we observed during the 2010 earthquake. And that's what we use for damage control. We have to check that our walls go no beyond, the strength does not go beyond 0.8%, like I mentioned. The effective R factor is somewhere in between 5 and 1 and 5, up to 5, being the largest one around 0.5 seconds, which is the area of major damage observed. The minimum base shear limitations, depending on the seismic zone 3, which is the highest, is 6.7% of the weight of the building, and in zone 2, which is Santiago, is 5% of the weight of the building. And the inner-story drift, which has to be verified for reduced forces by R, we cannot go any further than 0.2% at the center of mass, and an additional 0.1% at the perimeter, considering rotation, plant rotation. Here, to the right, is a typical graphic that we do to check how the compliance to this requirement is. I don't want to take more time on this. How that it works for us, the code, simply you can see the blue curve there is the code elastic spectrum for accelerations. That is for a single degree of freedom. The elastic response of real building would be the purple dots there because they are multi-degree of freedom. And then we divide those values by R, and we have to check that we cannot go below the minimum base shear, which is the green line there. And that there we get the red dots, which represent the accelerations for a design. Now, if we move to the displacement domain, we can notice that, let's look at the blue line is the code spectrum, which it would be the blue line here. The green line represents the minimum base shear, which is represented here by the parabola there, the green one. And so when we design for strengths here, which are the red dots, what we get is displacement of the red dots in this graphic. So the question is, when we have to, in those instances, we are having elastic response of the building. But if we have to check damage in the delta U, which is quite above the green line, the question is, by pushing your structure up to delta U, how much ductility are we requiring for those buildings? Because at a certain point of displacement, you will move from elastic into inelastic behavior. So one of the things that we have done, in this graphic, we know what delta U is because it's defined by the code. We know what delta D is because that's design displacement. We don't know what delta Y is because we seldom know it. We would have to do a pushover analysis or something like that. But we can assume that values between 2 and 3 that have been historically reported, if we take conservatively a value of 2, we can do an estimate, a reasonable estimate of what the required displacement ductility to go from design to delta U displacement. And we can see on this graphic to the right that values between 1 and up to 6 being the large, I mean, in general, they are no larger than 4, but around 0.5 seconds, you get higher than 4. That means, again, identifies the area that has to be studied and maybe updated in future versions of the code. Just a few examples of high-rise buildings that have been produced by using all of these philosophy, local and local code. This used to be the tallest building in a very complex building in Santiago, Telefónica buildings. This is the Costanera Center project that David just mentioned at the beginning. It comprises 4 buildings, out of which the tallest one and the smallest one is built. The other one are built up to the 10th floor for the moment. It is a very iconic building. Probably if you go to the internet and ask for Santiago, the first thing that will come up is some of the pictures that you are seeing here. Some very iconic buildings and very irregular buildings, like I was telling you, and many, many conventional structure like the one you see here. Now let's, okay, and this is another example of it's not really a building for residential or office. It is an industrial facility, a solar thermal tower plant, which has a central building, let's say, of 250 meters high to collect all the reflected sun from the mirrors. That is finished as a structure, but the project is still under construction. Now, if we move into protection system, we will realize that, I mean, in Chile, we have a special code for designing buildings with seismic isolation. We are almost done with a seismic code for energy dissipation devices. It's already written, it's under final discussion. But in any way, in those cases, you still have to comply with the 2 codes that apply to general buildings, which is NZSEE and NCH 433 and 61. The first base isolation system that was built in Chile was in 1992. It was a 3-story building of confined masonry. They were built 2 buildings identical, one with base isolation and one without. Both buildings were instrumented in order to record and be able to compare what were the difference in behavior during strong earthquake. All of those results have been published by University of Chile, which was behind this idea. Then after that year, base isolation started to be used mainly on private hospitals. And nowadays is a standard requirement in any public hospital and in private as well. In 2010, when the big earthquake came in the area affected by the earthquake, 15 structures had seismic protection system, 14 of which were buildings and 1 was a bridge. And the important thing to mention is that all of these structures perform extremely well, which is well recognized by people. And so, and developers saw on this an opportunity, a marketing opportunity by incorporating this technology into their newer buildings. And it is important to know that the majority of the technologies used in seismic protection up to this year were locally developed as a result of research on the 2 principal universities, which is University of Chile and Catholic University. Nowadays, we already have designed and built a little over 100 buildings with seismic protection systems. Here's a graphic where you can see in the horizontal line number of stories from 1 up to 52 stories, and on the vertical line the number of buildings. And you can see in color what are the different type of systems used. The important thing is that 75% of those buildings, which is a little over 80 buildings, use base isolation. 18% use tune mass damper. Tune mass damper is something that we are doing, but we don't like to do it. Tune mass damper is much closer to doing nothing, but it is the cheapest solution, and developers usually require that because of marketing reasons for their projects. So we have to do it. Another system is only 7%. So here are some images of the buildings that we have designed with these technologies. This is Ñuñoa Capital, which is the tallest residential building base isolated in America. It's 33 stories high. It's already finished. It hasn't experienced a strong earthquake yet, but some small, yes, with nothing unexpected. Example of buildings that use TMDs. Usually TMDs are large masses placed on top of the buildings, between 1% and 2% of weight of the total building, sitting on isolators, lead rubber bearings or rubber bearings or whatever. Here's a pendulum TMD system with energy dissipation devices, which is was finished last year. Energy dissipation system like viscous dampers in office buildings have been used many times. This is the tallest building with some kind of energy dissipation system, which is a titanium tower, a 52-story tower. This one experienced the 2010 earthquake with absolutely no damage. These are the type of metallic dampers that were used on that project, and the blue lines on the plan there represent the places where are located these braces. And this is something different in a way that it's not located in Chile, it's in Lima, Peru, but it's a project that we have been working related to retrofitting. We don't do much retrofitting in Chile. Actually, we're always concentrated on new projects. And when I say we, it's not our firm only, but most of the structural engineering community. It has to do with 8 reinforced concrete buildings that were designed in the 70s that didn't have any special detailing, seismic detailing, so the owners wanted to improve stiffness, strength, and hopefully add some energy dissipation capacity. And after trying different alternatives, the building would have to be retrofitted, being used at the same time with the people living and using them. So the use of BRBs proved to be very efficient, and that's what's being implemented at this moment. And okay, let's summarize what I have presented here. In the quest for resilience, successful seismic performance starts with the selection of the structural system. This is a major point. Then life safety and resilience are different objectives that require different approaches to be solved. The problem historically is that usually the structural engineers have thought that by designing for life safety, they have automatically solved the resilience problem. And now they're realizing that this is not true. So life safety in conventional structure has to do with ductility. And resilience has to do, in this case, as we have shown, with stiffness, which are different things. In conventional buildings, the adoption of steel lateral load system, which represent values of H/T, is an effective strategy to control damage and increase resilience. Seismic protection systems provide proven and cost-effective solutions to reduce damage and increase resilience. It is my thought, my thinking that today we have available the knowledge and the technology to provide to society safe and resilient structure. It's just a matter that what do we have to do in order to start using them and assure that to everyone. And the successful performance of Chilean buildings in the 2010 earthquake is a consequence of these last two strategies. Now, if we just final comments regarding to the Chilean practice. The Chilean practice favors the use of walls as the main lateral load system, with wall densities above 0.1%, which help us to reduce compression and shear on those walls. We use a lot of redundancy, as I mentioned, which increases the lines of defense. We use high stiffness values of H over T larger than 40 usually, which will reduce roof drift demand. We limit the maximum concrete strain because that way we were limiting structural damage. We try to avoid irregularities, but we are always detailing for ductility with the new version of the code. But what's important, very important, is that countries not only need modern codes, they must ensure that those codes are used by the construction industry. So code enforcement through mandatory peer review has proven to be of major importance. In our country, any building above 3-story has to be peer reviewed by someone else. And this is something we think not as a problem, but as an opportunity. I myself, as a practitioner, I really thankful that I have another colleague to look at my numbers, to look at my drawings, and I expect them to do a good and detailed job when do the peer review. So peer review has been in our practice for over 15 years, and that's something that I fully recommend. Thank you.
Thank you very much indeed, Renee. It's a fascinating story with a lot of similarities to things we've been finding out ourselves and I'm sure in different parts of the world. A story told from a wealth of experience in a highly seismically active country. Do we have some questions, please?
Please.
There's a microphone.
I have one simple question. You mentioned about isolated TMD structure, isolated TMD. So
yes.
Usually for isolated structure, in your country, in Chile, have you ever tried this kind of structure? Because in isolated structure, usually the story drift has been reduced, much reduced. So is this, sometimes if we add some other equipment, maybe device, maybe the cost will be much higher. Could be, what do you think of this?
Could you repeat that? I'm not sure I follow completely your question. Excuse me.
Was the question about the combination of using a tuned mass damper and isolation? Or?
I think he mentioned some of the TMD. Yes,
yes.
Tuned mass damper structure.
TMD is usually placed on top of the building.
Yes, you're right.
On rubber bearings. If I understand correctly, you additionally consider base isolation in the building on the lower part of the building? Is that?
Yes, yeah.
Yes, we have seen that in Japan they have used on certain occasions that kind of solution. We haven't tried it yet.
Okay.
Probably if we're able to use base isolation, that would be more than enough for a building. And you would not, I mean, the problem with the TMD located at the top of the building, it has to be tuned.
Okay.
If you think of concrete, the concrete modulus of elasticity, it changes over time. So over the years, probably it will become out of tune. Additionally, if you think of the movement after several earthquakes, also the natural period of the building would change. So you might end up with something that was very well tuned at the beginning, and after many years, maybe it's out of tune, and who's going to take care of that? So it's very risky, but that's one of the reasons, and that we don't like to do that, because it's more for marketing reason rather than really effective. Besides, you get a much higher reduction in the response of the building by using isolation or energy dissipation than what you can get at the best cases of TMDs.
Okay, thanks.
Any other comments or questions? Yes, Peter.
Renee, thank you for an excellent presentation. My question is related to measuring the performance of buildings. Can you give us some brief comment on how you would now recommend measuring performance of such buildings?
That is a good question and a very tough one. Because what is performance? It depends. You can look at it in several different ways. How much damage you collect, how much money you spend in repairing, or how much money you spend in trying to avoid that as a strategy. Actually, I just showed you a couple of indexes trying to look at the problem from different points of view. But I don't think there's a common way of measuring it, performance. All I can say that in the common sense of people who lives on buildings, performance has to deal with not having their life broken up because of problems in their housing. They want to go on living there, hopefully with nothing happen. And that is performance to common people, and that's what we're trying to find ways to measure that. It's not a simple thing, but we have to move into that direction. We structural engineers have to somehow match with people's expectations. People don't care about numbers. They care about what they get. And what are the indexes that we must use in order to be able to deliver what people expect? It's a tough question. Okay.
David, can I ask a supplementary?
Okay, one more.
How many of the buildings we see in the picture, the beautiful picture, are instrumented?
We try to get instrumentation in those buildings as much as we can. How many, I'm not sure, but there might be, I don't know, some maybe 50 buildings or something like that. There's a lot of efforts from the universities to do that. The problem usually is that the owners are not willing to accept that, to have those type of instruments. But the first question they ask, what do I win with that? I am exposing myself to, if something is not according to the numbers, and I know it, legally I'm forced to do something to solve that problem. And if I don't know it, I'm not forced to nothing. So I'd rather not know. Because statistics tell us that things in general behave well, so why care? Many of the people that accept doing that is just because of they are some emotionally involved in research or maybe in doing some improvement to society. But it's not a common issue. Usually what we get is many in buildings that belong to firms that want to represent social responsibility. They are willing to do that because in a way they're going to use it as marketing. There's nothing free on all this trade.
Thank you. I sense Peter's trying to promote more instruments and buildings. So all that remains, I think we were going to cut it here now because time is up. So what all remains for me to do is thank Renee for coming so far and sharing his wonderful experience with us. And we have a small gift as a token of our appreciation, which is a little bit of New Zealand art that you can take home and hopefully remind you of your trip here and your presentation.
Thank you so much.
Thank you.
Thank you.